Hello, we are Biomedical Engineering Senior Design Team 8, and our project is the Hospital Washer Auto Sampler. Hospitals around the world use large, high-temperature industrial washers to clean and sterilize surgical instruments. There is a wide variety of wash cycle protocols due to variability in water quality and industry standards. For example, in some parts of Europe, hospital standards suggest wash solutions with very high pH levels, which can potentially damage the surface properties of some Stryker devices. For this reason, Stryker is interested in providing hospital washer technicians with the tools and information required to select appropriate wash protocols for their products. To solve this problem, a Stryker engineer developed a prototype auto sampler, a device designed to periodically obtain fluid samples from the wash environment, which could then be manually tested for pH and conductivity levels. Our team was tasked with improving the ease of use of this auto sampler as well as the chemical sensing capabilities of the device. Feedback from technicians working with the device suggested that it was difficult to use as it required the technician to measure and tabulate the data manually. To account for this, Stryker suggested the possibility of a wireless device which could measure properties of the wash environment and transmit data to the user live throughout the wash cycle. This was the idea our team decided to pursue. We chose to use an Arduino Mega to control the sensors and a Bluetooth transmitter to send data to the user's device. 5 sensors were selected to be incorporated into the device: temperature, pH, conductivity, which is associated with water hardness, oxidation reduction potential, which is associated with water quality, and an accelerometer to sense phases of the wash cycle. To complete our design objectives, the sensors had to be incorporated in a circuit with the Arduino and Bluetooth transmitter, so we designed a printed circuit board to include the sensor ports and their corresponding chips, and programmed the Arduino to control the sensors and the Bluetooth transmitter. In order to protect the electronics in the device from the near boiling water used in hospital washers, we had to create a waterproof and heat-insulated housing. With this in mind, we designed a 3D printable housing with a 2-layer design to allow the inclusion of a pyrogel blanket insulation. Waterproof cable glands and a rubber gasket and clamps were used to seal the housing while allowing the sensor cables to extend into the wash environment. The housing was printed in Ultem by our sponsor at Stryker. Our primary design objective was to improve the ease of use of the device, so we wanted to give our sponsor an idea of what a user interface for displaying sensor data and alerting the user of damaging washer conditions might look like. We interviewed a washer technician at Stryker to get a sense of what features should be included. Our team created an outline of the menu structure and an interactive mock-up to illustrate our ideas, which Stryker can use in the implementation of the app. Our plan was to complete a series of tests with the prototype in a Stryker high-temperature hospital washer, but this became infeasible due to safety concerns related to travel. Instead, we performed tests in a home dishwasher to demonstrate waterproofing, sensor functionality, and Bluetooth functionality. We also investigated the possibility of FEA simulation to estimate the performance of the device in hospital washer temperatures or locate problem areas in the housing design. Future work on this project could include additional sensor testing with common washer solutions, an FEA simulation of the housing with accurate thermal loads, and high-temperature testing in a hospital washer to assess internal humidity, temperature, and sensor function. Lastly, the implementation and usability testing of the mobile app is necessary to complete the device. We would like to thank everyone at MTU and Stryker who helped us complete this project.